So going to take similar. Listen carefully. So f of x here is 1 minus mod x. 1 minus mod x. It is exactly similar to the previous sum what we saw. F of x is equal to a minus mod x. Alright, the previous sum what we saw is f of x equal to a minus mod x. There we had a limit as mod x less than a. Am I right? We had a limit mod x less than a. So we expanded this as minus a to plus a. We expanded this as minus a to plus a. And we solved that problem. Here it is f of x is equal to 1 minus mod x. F of x is equal to 1 minus mod x, where the interval is if mod x less than 1. You know very well. As we discussed here, if f of x is less than a, we write minus a to plus a interval. Similarly, this can be written as minus 1 to plus 1. This can be written as minus 1 to plus 1. The next function for the remaining, that is if the f of x is greater than 1, which is 0. It is given as 0. So we have to deduce what is this. Actually, in this problem, we have to solve f of x of Fourier transform, and we have to deduce two things there. One is similar to the previous problem. Previous problem, similarly, we had like this 0 to infinity sin t by t whole square is y by 2. And the next one is 0 to infinity sin t by t whole power 4. For the second part, we will be using Parseval's identity. It's a separate concept we are going to see now. That is for the second deduced part. So, like as we saw in the previous problem, the procedure is same. First, what is the first thing? You have to take what is the function. So here you have the function f of x is 1 minus mod x. The interval is minus 1 to plus 1. Interval is minus 1 to plus 1. The interval is minus 1 to plus 1. So here, what is the Fourier formula? Fourier formula. F of x is equal to 1 by root 2 by integral minus into reciprocity f of x e power isx dx. So this is the formula. So in this, what we do? We substitute what the function given. So here 1 by root 2 by integral. Here the limit for this function is minus 1 to plus 1. So minus 1 to plus 1, f of x is 1 minus mod x e power isx. E power isx can be rewritten as cos theta plus sin I sin theta. Here it is sx. So cos sx plus I sin sx. The previous case we had minus. So we had cos sx minus I sin sx. Here it is positive. So we have plus term here. So dx. Now, at present, so this is the scenario. Here, what we have to check? This is a very big term here. So, in order to reduce this and also to remove this modulus, what we did in the previous one? Yeah, we saw which is even and which is odd. I told you a minus mod x is an even function because it is very well known thing, that is a is a constant, mod x is an even function. So, the entire term is an even function. So here cos x is even. So even into even is even. But when you take about sin is an odd function. So even into odd it becomes odd function. So we just omit this because minus 1 to plus 1 of odd function is 0. It may be anything, minus a to plus a, minus 2 to plus 2, whatever the limit. But if it is minus a to plus a format, the odd function integration is 0. So we take 1 by 2 pi, that is root 2 pi integral minus 1 to plus 1. Here since we take only the even part, modulus x can be written as 1 minus x. Then cos is x dx. So I can write 2 here and I can put 0 to 1. Now right, because the even function, as per the property of integral, you can write minus 1 to plus 1 for an even function. It can be written as twice 0 to 1. So what formula we will use here? Bernoulli's formula. So by using Bernoulli's formula, so we get the answer f of x is equal to, by using the Bernoulli's formula, what we get. So here we have this is u, 1 minus x is taken as u and dv is taken as cos sx. So when you solve this, when you solve for Bernoulli's formula, you get the answer as, go down. So by using Bernoulli's formula, so by substituting in the UV minus U dash equal expansion, then you have to try this expansion. So you get the final answer as what? What is the final answer? 2 by root 2 by. This you can repeat. What is that? Minus cos S by S square minus cos S by S square plus 1 by S square. So by using Bernoulli's formula, by using